So in the last video, I discussed the stability of the fixed points and the stability thereof of this system of equations, dx dt is equal to x minus y, and dy dt is equal to x squared minus 4. We found that there were two fixed points, one at the point 2, 2, and the other at the point 2, minus 2. And we then studied the stability of these fixed points, and I argued that the stability was determined by the system, by this 2 by 2 system of equations. So now what I want to do is solve these equations for you and start to piece together a picture of how the solutions of this general nonlinear system behave. So the first step, which is what we're going to do on the next, is we're going to actually solve for the stability of these two fixed points. I'm going to start with a blank page to make this a little bit easier, and we're going to just write out d delta dt, and let's consider first the fixed point at 2, 2, so x equals 2, y equals 2. And so according to what we just wrote down, the matrix is minus 1, 1, and then it was 2x, so x is 2, so that's 4, and then 0 times delta. So this is our matrix A, and you remember from class that what we have to do to compute the fixed points is to solve the determinant of A minus lambda I is equal to 0, and the characteristic equation for this is just lambda squared minus lambda, plus 4 is equal to 0, which has roots. The quadratic equation has roots. Lambda is equal to a half times 1 plus or minus, and let's see, 1, so the square root of 15i. These two eigenvalues have both a real and imaginary part, and the consequence of that is that the solution, if we just remember the general solution that I described in class, is that y is equal to c1 times v1, where v1 is the eigenvector associated with the eigenvector v1, times e to the lambda plus t, actually let me call this v plus, plus c2 v minus e to the lambda minus t, where lambda plus minus, as I just said, were a half times 1 plus the square root of 15i. So this is an example that we discussed in class, and you remember that when there's both a positive real, and an imaginary part, then what that means is that e to the lambda plus t, and this is also true for e to the lambda minus t, has the general form e to the t over 2 times some combination of cosines and sines. So cosine the square root of 15 t plus or minus for the minus, the sine I times the sine of the square root of 15t. So therefore, the general solution for this problem for y can really be thought of in a little bit of a different way. Namely, I'll use a different color to emphasize that this is a bit of a conclusion. Really, what we're talking about is that y is equal to so the general solution is going to be a combination of something which is exponentially growing, namely e to the t over 2, times basically something which is proportional to the cosine and something that is proportional to a sine. So this type of fixed point, that is a fixed point where there's a positive real part and an oscillations, is what people call an unstable spiral. So unstable spiral. And the phase diagram I'll just draw for an unstable spiral looks something like this. So this is the x, right, and the y-axis. And basically, if the origin is the fixed point, you spiral away from the origin. There's also, of course, what one might stable spiral. And in a stable spiral, so a stable spiral, and for a stable spiral, then what happens, of course, is that there's also a spiral, but now the solution is the traction at the fixed point. And the difference between a stable and an unstable spiral is just the real part of lambda. So this actually has the real part of the eigenvalue less than 0, whereas an unstable spiral has the real part bigger than 0. And what we've now just learned is that the fixed point, so from all of this, is the fixed point at 2, 2 is an unstable spiral. So this is an interesting fact that we will use in a little bit. Okay, so now let's go to the second fixed point, which is at minus 2, 2. So the stability equation for that fixed point is given here. So what's changed actually is that the 4 that was in the lower left corner is now a minus 4. So the characteristic equation has a single sign change, but what we were about to see is that leads to a dramatic difference in behaviors. So the solutions of this quadratic are just 1/2 times 1 plus or minus, and now it's the square root of 1 plus 16. And so this, basically, these two eigenvalues, lambda plus minus, are both real. So these are both real, and 1 is positive, so lambda plus is bigger than 0, whereas lambda minus is less than 0. So this is a case that is analogous to something in class, in which the phase diagram for this type of a fixed point, I mean, if the stable direction were the x-axis, and the unstable direction were the y-axis, then this is what we call the saddle. So if this were the stable direction, then you would flow inwards in this direction, outwards in this direction, and so this is a saddle. So what we've just learned is that the second fixed point is a saddle. So now let's try to, now if we want to actually try to put this together and understand how to actually draw this, we need to actually understand what the directions of the stable and the unstable manifold are. And in order to do that, then we need to actually find out what the eigenvectors are. So, okay, so now we need to find actually what the eigenvectors are in order to proceed further. So we don't really need to find the eigenvectors for the spiral, the reason being that the solution, as we already showed, just spirals around. There's not really a direction. There isn't a direction, actually, where the velocity arrows are confined. So what we need is the eigenvectors for the saddle. Now, for the saddle, then the eigenvectors solve this equation where, of course, x star is minus 2, so this number is minus 4. And we can find the components of the eigenvectors v1 and v2 from either the first or the second equation here, but the easiest one to look at is the second, where we have lambda plus minus v2 is equal to minus 4, or no, lambda plus minus v1, actually, excuse me. It's equal, no, I had it right the first time. Lambda plus minus, here, let me erase, oops. Lambda plus minus v2 is equal to minus 4 v1. So this is v2. So this basically corresponds to the eigenvector 1 minus 4 over lambda plus minus. And of course, lambda plus minus, you will recall, were given by these nasty expressions that we had before. Lambda plus minus is equal to 1/2 of 1 plus or minus the square root of 17. So just because we're going to want to plot these things, it's useful to actually find out what the numbers are for these things. So for lambda plus, you can just plug the numbers in to a computer and find out what they are. And it turns out that this is 1, and then this is minus 1.56. And for lambda minus, the eigenvector is 1, and this turns out to be 2.56. So those are the two directions that we have. So let's just keep those in mind for a second to put everything together and actually draw a phase diagram. So I'm going to do this as best as I can. As you all know, I'm not a very neat writer. We have two fixed points. So we have one at the point 2, 2, which we'll draw here. And we have one at the point minus 2, which we can draw at the point here. And we've decided that the one at the point 2, 2 is an unstable spiral. So the one at the upper point here is an unstable spiral, whereas this one is a saddle. So let me actually just change the colors, and let's see if we can start to sketch what is going on here. So so if we go back to the eigenvectors, the positive eigenvector had you might recall from the last moment that I just said, had an eigenvector which was 1, I'm just going to write it down at the bottom, it was 1 minus 1.5. So that means that's the direction. So that's actually, when x goes up, y goes down. So that's basically this line. It's a line that looks like this, and along this line, the arrows, the velocity arrows, are unstable, and so it looks something like, here, let me see if I can do this. So it's something like the flow is going away along this, whereas the other line, which I wrote down, which was 2.5, So that's a line that looks something like this. So we go over by 1 and we go up by 2, so it's somehow a little steeper in that direction. So for that was the stable direction. So the arrows, were looking down like that, and so they're sort of going into the fixed point. So that's basically what we have now. And so and then on the other hand, we know that out of this fixed point, there's a spiral. It actually could be going to the left or to the right, and we know it's an unstable spiral, but let's just draw it like this. And now what we are faced with is the prospect of trying to piece together the flow diagram together. And this is the part which actually is a little bit hard. You can use MATLAB to do it, but there are a couple of other tricks that I'm going to show you on the next video.